So, picture this. You've just deployed your brilliant new app to the cloud.
Right.
The code is totally flawless, the UI is gorgeous, and all the unit tests passed with flying colors.
A rare feeling, but a great one.
Exactly. So you push it to production, you close your laptop, and you go to sleep feeling like an absolute engineering genius.
Only to be jolted awake at, 2 in the morning by a barrage of PagerDuty alerts.
Oh, the absolute worst.
It really is. Your application is entirely unresponsive, and a quick glance at your logs reveals your database is currently being held for ransom.
Yeah, or maybe it's quietly mining cryptocurrency for some server in Eastern Europe.
Exactly.
And you just sit there staring at the screen wondering how on earth it happened because, you used all the best coding practices, right? You've sanitized your inputs, you hashed your passwords.
But the thing you failed to consider, or you entirely forgot to design, actually, was the empty, invisible space surrounding that code.
The foundation, the network.
Yeah. It is the absolute classic trap for modern software developers. We become so, hyper-focused on the actual services we are building that we treat the network they live inside as just an afterthought.
Or worse, like it's someone else's problem entirely.
Right.
And if you've ever stared at an AWS console at 2 in the morning, wondering why your EC2 instance is completely unreachable.
Which I think most of us have.
Oh, yeah, definitely. Then you know exactly how painful it is when you get this foundation wrong. So today, we are custom tailoring a deep dive just for you, focusing entirely on that invisible architecture.
That's such a crucial topic.
It really is. And our roadmap for this is a brilliant narrative-style tech blog post by Aaron Rose. It's titled The Secret Life of AWS VPCs and Subnets Explained.
And, the author takes a really refreshing approach here. Instead of a dry, textbook-style technical manual, we are dropped into this grand Victorian library in London.
It's such a cool vibe.
Yeah. And we follow a junior engineer named Timothy who brings this architecture diagram to his senior mentor, Margaret.
And it is such a relatable setup, honestly. Timothy arrives with this piece of paper showing his web servers, his S3 buckets, his database.
All neatly boxed out.
Right. He's got them all boxed out and connected with these decisive little arrows. And I have been that developer. There is something incredibly therapeutic about standing in front of a whiteboard and just drawing the boxes.
Oh, we all love the boxes.
Right.
They represent the tangible, satisfying parts of the job, right? It's the stuff you build.
Exactly.
But Margaret, who is playing the role of the seasoned cloud veteran here, she just ignores the boxes completely.
Just totally dismisses them.
Yeah. Instead, she taps the blank space on the paper between the boxes. She points out that the white space on his diagram dictates absolutely everything those boxes can and cannot do.
Okay, let's unpack this, starting with the biggest piece of blank space on Timothy's diagram. Margaret introduces him to the concept of the VPC, the virtual private cloud.
Right, which sounds like a bit of a marketing buzzword, honestly.
It really does.
But technically speaking, it is the absolute perimeter of your infrastructure. When you create a VPC in AWS, you are essentially staking out an isolated mathematical boundary inside their massive physical data centers.
So you're claiming your territory.
Exactly. You are defining a specific block of IP addresses, which is commonly referred to as a CIDR block.
I always think of the VPC like buying an empty plot of land and building the thick exterior walls of a concrete fortress.
That's a good way to look at it.
Right? You have a footprint now, you have an interior and an exterior, but at the moment you build it, there are absolutely no doors and no windows.
The concrete fortress is a really solid way to visualize it because, nothing gets into that CIDR block and nothing leaves that CIDR block unless you deliberately engineer a pathway for it.
It's totally sealed.
Right. And the frustration for many developers as they spin up their beautiful application inside this fortress, try to load it in their browser, and get a completely dead page.
Because they forgot to cut a door in the wall. It's funny, too, because AWS aggressively markets themselves on this military-grade, airtight security. Yet Margaret points out a rather massive caveat to Timothy in the story.
Yeah, the default settings.
Yeah. Every AWS account automatically comes with a default VPC in every region, and that default environment is basically a fortress with the gates completely blown off their hinges.
What's fascinating here is the paradox between developer friction and actual security.
Oh, totally.
If AWS handed you a perfectly secure, windowless concrete fortress on day one, you would hit a brick wall of networking configuration just trying to run a basic Hello World tutorial.
Right, you'd spend 3 days just trying to get a ping through.
And you'd quit out of frustration.
That,
So they prioritize making the first 5 minutes as frictionless as possible.
which makes sense from a business standpoint.
Sure, they build the default VPC so that every resource you place inside it has a direct, unimpeded route to the public internet.
Which is fantastic for like a 10-minute weekend experiment.
Oh, it's great for that.
But it's a massive systemic vulnerability the second you start handling real user data or deploying production code. I mean, the default VPC essentially collapses all your architecture into one giant street-facing room.
Exactly. Everything is just out there on the sidewalk.
Okay, so if we shouldn't use the default one-room warehouse, how do we actually structure a production environment? I mean, we need interior walls, right? We need to subdivide that massive block of IP addresses into functional areas.
Yes, and this is where subnets come in. A subnet is, well, it's simply a smaller slice of your VPC's total IP address range.
Just breaking up the land.
Right.
Yeah.
But in the cloud, these logical slices are also tied to physical reality. AWS forces you to place your subnets into specific availability zones.
Right, because if an entire AWS data center in Virginia loses power or, gets its fiber optic cables severed by a backhoe,
Which happens more than you'd think.
it really does. You don't want your entire application going dark. So you spread your subnets across multiple physical locations to prevent a single point of failure.
Exactly. And beyond the physical redundancy, subnets give you logical control over exposure. Margaret introduces Timothy to the concept of public versus private subnets.
Okay, break that down for us.
So a public subnet is configured with a route to the internet. A private subnet explicitly lacks that route.
See, if I'm building a modern web application, my instinct purely from a developer perspective is to just throw my app servers and my database on the internet and lock them down with really strong passwords.
A lot of people do that.
Right. Why go through the massive headache of creating these separate public and private rooms?
Well, because passwords get leaked. I mean, software vulnerabilities are discovered daily. What you are describing is a brittle perimeter defense.
A hard shell with a soft, gooey center.
Exactly.
Yeah.
Once an attacker bypasses the password, they just have the keys to your entire kingdom. Margaret advocates for what we call defense in depth.
Okay, let's trace how that layered architecture actually handles traffic in the real world.
Sure, you start at the outermost layer, the public subnet, and the only thing you place in this street-facing room is your load balancer.
Just the load balancer.
Just the load balancer. Its sole purpose in life is to accept incoming traffic from the internet and pass it along.
So the load balancer is kind of like the greeter at the front door.
Yes. Then you create a private subnet, an interior room with no internet access, and place your application servers there.
Okay.
The load balancer takes the incoming request from the public internet and hands it to the application server in the private subnet. The outside world can never talk to your application server directly.
Wow. And the database, where does that sit in this model?
The database goes into an even deeper private subnet, layer 3.
Oh, wow.
Yeah, it is completely walled off from the internet, and it's also walled off from the load balancer. It will only accept traffic coming directly from the application servers.
Okay, I see the power of that. If a hacker exploits a vulnerability in your load balancer, they don't immediately get your user data.
Not at all.
They find themselves trapped in an isolated room, staring at another locked door leading to the application servers. They have to orchestrate multiple sequential breaches just to reach the database.
It basically turns a single point of failure into an obstacle course. But this extreme isolation introduces a massive functional problem.
Here's where it gets really interesting. I've locked my database in a windowless interior private room. It is beautifully secure.
Very secure.
But what happens when that database needs to download a critical security patch from a vendor's website? Or what if my application server needs to ping Stripe's API to process a payment?
Right.
If they have absolutely no route to the internet, aren't they completely cut off from the outside world?
They are, unless you engineer a highly specific door just for them.
Okay.
Margaret introduces the concept of gateways to solve this exact problem. And she specifically contrasts the internet gateway with the NAT gateway.
The internet gateway makes sense to me. You attach it to the edge of your VPC, and it acts as the main two-way street for your public subnets. Traffic flows in, traffic flows out.
Exactly.
But our private subnets aren't allowed to use that street.
Right. So to give the private subnets access without exposing them, you have to deploy a NAT gateway. NOT stands for Network Address Translation.
Network address translation. Got it.
And its placement in the architecture is critical. You must place the NAT gateway inside a public subnet.
So it sits in the street-facing room, acting as a proxy for the interior rooms.
Yes.
How does the translation mechanism actually work under the hood, though?
Well, let's follow a packet of data. Your database, sitting in a private subnet, generates a request to download a software patch. That packet has a private source IP address, say 10.0.1.5.
Okay.
A private IP is non-routable on the internet. If it hit the open web, routers would just drop it immediately.
Because millions of internal networks use that exact same 10 dot address.
Exactly. So the database sends the packet to the NAT gateway. The NAT gateway intercepts it, literally strips the 10.1.5 private IP address off the packet, and slaps its own public IP address onto it.
Wait, literally strips it off?
Literally strips it off and replaces it. It then sends the packet out to the internet through the main internet gateway.
And when the vendor server sends the software patch back, it addresses the reply to the NAT gateway's public IP.
You got it. The NAT gateway receives the file, checks its internal state table to remember who originally asked for it, swaps the IP addresses back, and quietly hands the patch to the database in the private subnet.
It operates like a one-way mirror, or like a highly secretive concierge.
That's a great analogy.
The database can reach out into the world and get what it needs, but nobody on the outside internet can initiate a connection inward. If a malicious bot scans the NAT gateway's public IP and tries to connect to the database, what happens?
The NAT gateway simply drops a connection. It only allows return traffic for requests that originated from the inside.
It is an incredibly elegant mechanism for keeping resources invisible while still letting them function.
Very elegant.
But Margaret delivers a rather brutal reality check about this elegance in the story. She drops 2 words on Timothy that strike fear into the heart of any cloud engineer.
Oh yes, the meter.
The meter, because an internet gateway is essentially just a logical router, right? AWS provides it, and you really don't think about it from a cost perspective. But a NAT gateway is a fully managed, highly available service.
And AWS bills you for it accordingly. They charge you an hourly rate just for having it turned on, plus a data processing fee for every single gigabyte that flows through it.
It's the equivalent of hiring an expensive 247 concierge for your building.
Exactly.
If you are running a production environment handling live user data, you absolutely pay the concierge. The security is non-negotiable.
Oh, absolutely.
But if you spin up a NAT gateway for a quick weekend sandbox project and you forget to tear down the infrastructure,
you will receive a deeply unpleasant surprise on your credit card bill 30 days later. You just paid a premium concierge to stand in an empty hotel for a month. It really underscores a harsh truth about cloud computing. Architectural decisions are inextricably linked to financial decisions.
That is such a good point. Okay, so we've mapped out the major infrastructure. We have the CIDR block defining our exterior walls. We have public and private subnets acting as our rooms.
Right.
We have internet and NAT gateways functioning as our doors. Now we have to talk about the actual traffic cops. How do we define who is allowed to walk through those doors and access specific resources?
That brings us to the 2 distinct layers of access control in AWS: security groups and network access control lists, commonly referred to as NACLs.
These 2 mechanisms constantly trip developers up. I mean, I have personally spent hours debugging failing connections entirely because I confused how these 2 systems evaluate traffic.
It's a rite of passage, honestly.
So let's break down the mechanics, starting with security groups.
Okay, so security groups operate at the individual resource level. You don't apply them to a subnet. You attach them directly to a specific EC2 instance or an RDS database.
So if the subnet is the room, the security group is the lock on a specific piece of furniture inside that room.
Yes. And the defining characteristic of a security group is that it is stateful. It remembers the context of a connection.
And stateful behavior is so crucial for troubleshooting. I like to think of a security group as like a modern hotel keycard system.
Okay.
You use your keycard to unlock the door from the outside and walk in. When you want to leave, you don't need to swipe your card again. You just turn the handle and the door automatically lets you out. The system inherently trusts the return trip.
That's spot on. In networking terms, if you write an inbound rule allowing traffic on port 443, the security group automatically permits the response traffic back out to the client, regardless of your outbound rules. It remembers the state.
NACLs, on the other hand, operate entirely differently.
Very differently. NACLs are applied at the subnet level. They act as a boundary checkpoint before traffic even reaches the individual resources in the room. And crucially, NACLs are completely stateless.
Stateless meaning they have absolute amnesia.
Total amnesia. A NACL evaluates every single packet of data in total isolation.
Wow.
If you allow a request in, the NACL does not automatically allow the reply back out. You have to explicitly write a matching outbound rule to permit the return traffic.
It is the equivalent of a border checkpoint with two entirely separate toll booths.
Yes.
Getting your passport stamped and paying the guard on the way into the country means absolutely nothing. When you turn around to leave, you face a different guard, and you have to present your papers and pay a toll all over again.
Which leads to Margaret's fantastic philosophy on troubleshooting network issues. She tells Timothy that networking problems are incredibly frustrating because they are binary.
Right. The traffic either arrives or it doesn't. You rarely get a helpful application error that says, hey, I failed to authenticate at the database. The connection just vanishes into a black hole.
And finding that black hole requires methodical elimination because your traffic has to successfully traverse both systems. An incoming packet hits the stateless NACL first, and if it survives, it hits the stateful security group.
Right.
Both systems must permit the traffic, but either system can silently destroy it.
So what does this all mean? Here is the absolute aha moment for anyone listening who has to debug these issues. Because of the way these systems handle rejected traffic, they leave different forensic clues.
Let's look at the symptoms. If you try to SSH into a server and the connection instantly rejects you, just immediately fails, you should look at your NACLs.
Okay.
Stateless firewalls often actively drop packets and send back a rejection message, which causes an immediate failure on the client side.
But if you try to connect and your terminal just hangs and hangs and hangs until it eventually bleeds out and dies of a TCP timeout, it just times out.
Then you check your security groups. By default, when a security group blocks a packet, it doesn't send a rejection notice. It just sullenly discards the packet into the void.
Just throws it away.
Yep. Your client has no idea it was blocked, so it just sits there waiting for a reply that is never coming.
Immediate rejection versus a hanging timeout. That one distinction alone will save you hours of pulling your hair out at 2 a.m.
Oh, without a doubt.
In reality, though, how do veteran engineers manage these two overlapping systems? Do you write identical, ultra-strict rules for both?
Generally, no. Managing thousands of stateless dual-direction rules on NACLs becomes a logistical nightmare very quickly.
I can imagine.
Industry best practice is to leave your NACLs relatively permissive. You use them as a blunt instrument.
A blunt instrument?
Yeah. Say a specific range of IP addresses in a foreign country is launching a denial-of-service attack against you. You use the NACL to instantly block that entire subnet block at the hallway door.
You drop the hammer at the perimeter?
Exactly. But for the nuanced day-to-day access control, deciding that this specific app server is allowed to talk to this specific database on this specific port, you rely on the smart, stateful security groups.
This entire journey through routing tables, gateways, and stateful firewalls highlights a brilliant quote from Margaret near the end of the text.
It's a great quote.
When discussing why so many companies end up running production workloads in wide-open default environments, she calls the default VPC the pet that wasn't supposed to become a pet.
It perfectly encapsulates the insidious nature of infrastructure debt.
Yeah.
An engineer spins up a default VPC because they want to test a proof of concept without friction. It's fast, it works, and they plan to tear it down later.
But then the proof of concept succeeds. Management likes the feature. Marketing wants to launch it next week. The developer bolts on a database, adds a load balancer, and suddenly real customers are logging in.
And that quick, dirty, completely exposed sandbox organically mutates into a mission-critical production environment. Nobody ever went back to properly architect a foundation because the application code was already working.
Margaret looks at Timothy and says, an hour now or a problem later.
Such good advice.
It really is. Sitting down to map out your CIDR blocks, isolating your private subnets across availability zones, configuring your NAT gateways, and tightening your security groups. While it takes genuine effort, it might cost you an afternoon of configuration before you write a single line of application code.
But that afternoon of foundational work fundamentally alters the security posture of everything you build on top of it for years to come.
We see this realization wash over Timothy at the end of the narrative. He takes that original diagram, the one with the neat little boxes and arrows, flips a paper over, and starts again.
But this time he draws a large rectangle first. He labels it VPC. He slices it into subnets. He marks the public boundaries and the private interiors. He places the gateways on the perimeter.
Only after the environment is fully defined does he finally draw the application boxes, tucking the database safely away in the deepest private room.
He finally gets it.
He does. He finally understands that the network isn't an annoying hurdle standing between him and his code. The network is the environment that grants the code permission to exist.
It requires a profound shift in mindset. You have to stop viewing the cloud as simply a magical server farm where you upload files,
Right.
and start viewing it as a hostile landscape where you must deliberately engineer your own gravity and atmosphere.
If you leave that invisible space undefined, you are abdicating control of your application's fate.
Completely.
As we wrap up this deep dive, there is a fascinating psychological angle to all of this that extends way beyond AWS architecture.
The tension between friction and safety.
Exactly. We discussed how cloud platforms default to total public exposure simply to eliminate the friction of getting started. They know that if they force you to define your boundaries up front, you might get frustrated and leave.
Right.
They prioritize immediate, unearned convenience over essential boundaries.
Which is an incredibly effective business model for user adoption, but it's disastrous for long-term stability.
It makes you wonder, though, if the absolute foundation of our digital infrastructure is designed with this inherent bias toward frictionless exposure, where else does this happen?
That's a good question.
Think about the apps we download, the smart home devices we blindly connect to our Wi-Fi, or the personal data we casually hand over to platforms.
We constantly accept default wide-open configurations because hitting next agree is easier than reading the permissions.
We trade essential boundaries and long-term security just to get the immediate dopamine hit of a working product. We let the invisible walls stay invisible because drawing the boxes is just so much more fun.
It always is.
It's definitely something to consider the next time a platform tells you the setup is completely seamless. What empty space are you failing to define?